Hello and welcome back on our discussion of modeling methods. And so now, having looked at a black box approach, I now want to switch our attention in looking at one of the gray box approach. I should mention at this point that in general, if we look at this diagram, right, we have this black box approach. Remember, I gave the analogy of you putting your hand into a box and you feeling around that box and you pulling something out and you have a result in your hand, but of course you don't know exactly how you got to that particular result. That's a black box approach. At the other end of that spectrum, if you like, we have another set of modeling methodologies, and that's classified as a white box approach, right? So for those of you who are religious, the analogy here is that you've had an epiphany, right? So you've seen the light, right? So a white box approach is simply that. It is largely a experimentally based approach, one that involves experimental testing, characterization, simulation, and that gives you some substantial physical understanding as to what is taking place and why. And again, some of that knowledge-based approach, that white box approach, would have been coming from the electron microscopy investigations that I had alluded to earlier in the case of recrystallization as well as precipitation. But these are quite intensive methodologies. They take a lot of time, and at the end of the day, although you know a lot of information, that information is limited, and the limitation of that is by the composition as well as the processing conditions. In the middle between this black box and white box approach, we have shades of gray, and so this brings us into our gray box modeling strategies, methodologies. And so the first one that I want to talk about is one that is based upon some semi-empirical equations of states. And indeed, all of us at one time or another, in one paper or another, would have come across these. And so here's some typical formulations for semi-empirical equations of state for, in this case, static recrystallization. And both of these expressions come after the work of my esteemed colleague Mike Sellers, where in this case he has the time for 50% recrystallization as well as the final recrystallized grain diameter, and how these two parameters are affected by either the amount of strain given by epsilon, or the initial grain diameter, d sub 0, as well as the Zener-Holleman parameter, z. The other terms, so the first terms, things like grain diameter, strain, all of these are physically measurable parameters, and so there is some physical understanding associated with these particular equations. However, we refer to them as being semi-empirical is because some of the other constants, such as A, M, P, U, right, as an example, they are all sort of curve-fitting functions. They are constants that we use simply because it enables this expression to fit the data. In terms of physical meaning, physical understanding, there may be some physical meaning there, although we simply at this point in time, we don't understand it. So there is this semi-empiricism involved in these formulations. And indeed, if we take this data and this sort of approach, and we fit it to some measured experimental data, here's such a result. And this comes after, again, the work of my colleague Mike Sellers, where He's plotting a number of things here. The grain size as a function of time, as part of the production route, say during the rolling of a carbon manganese steel. So these locus of points here represents the individual deformation passes and the strain involved as a function of each of those passes, and how that takes place with decreasing temperature, and the influence that that would have on the evolution of microstructure, in this case in the form of the austenite grain size. And so we can see, dropping out of the reheat furnace, we have a grain size on the order of just over 600 microns. As we begin to deform that, obviously we introduce a deformed structure. We see microstructural refinement through this periodic and systematic variation between deformation and then recrystallization. And then eventually we lead to some final grain size at the end of the day. The point here is that the semi-empirical equations developed of the form that I had mentioned earlier, they tend to fit the measured data rather well. And so that's very useful for us. But again, the limitation is that we don't exactly understand all of the physical attributes responsible for that particular model. So there's some element of uncertainty. Another way, another application, if you like, is looking at plate rolling. In this case, plate rolling of microalloyed steel, where again we're plotting the grain size as a function of time for a series of deformation passes. So the diamonds, if you like, represent the times at which the deformation passes would have been given from our roughing mill as well as our finishing mill, and looking at what happens to microalloyed steel, in this case where we have initially different starting grain sizes. So in spite of the fact that we have very different starting grain sizes, as we begin to deform, as the model predicts, then we see a convergence of these grain sizes, and again going through this periodic deformation, recrystallization response, leading to a final grain size, in this case, on the order of 60 microns. If we take this data and we look at other empirical expressions for the similar behavior, again, so we're looking, and now we're comparing other models in comparison to that of Sellers. So 3 other independent investigations created their own semi-empirical models, and one may say that when you look at collectively all 4 of these curves, there is a clear difference in terms of the path in which the model begins to predict the microstructure. So everything starts off the same, obviously at the beginning, right? Because that's known, that's understood, but the model, the individual models, take us on a slightly different path dependent upon each of those particular models. But one of the interesting points of this is the end point, that is the end microstructure that each of the 4 independent models predicts is remarkably the same. So irrespective of the path, and because these are semi-empirical models, we don't really understand completely, the path dependence, because a lot of the parameters of each of these 4 models we don't have any physical basis for. We simply fit the data to a curve. So in spite of this difference and this uncertainty, if you like, One thing that is certain, and that quite nicely all 4 models do predict, is the final recrystallized microstructure, and that's quite nice. We have yet other semi-empirical models related to other aspects of the evolution of microstructure, and here's such one that looks at the transformation behavior of our steel as we transform from the parent austenite phase to the transformation product, in this case being ferrite. So we have a relationship, and that relationship is plotted on the diagram where the independent axis, the y-axis, indicates the final ferrite grain size in microns from the original austenite grain size in microns as plotted on the x-axis. And so we can see this functional dependency, and indeed if we fit a semi-empirical equation to this, then we have an equation of the following form, and this comes from my colleagues Mike Sellers and John Bynon, where the final ferrite grain size is going to be a function of the of some unknown constants like A, B, C, but they're going to be also a function of some known parameters such as the cooling rate, right? So dt represents the cooling rate, the initial grain size of the austenite, the amount of strain that would have been put into the austenite prior to transformation. So we have some physical understanding, but we have some other constants which we do not have physical understanding for. Nevertheless, the expression quite nicely fits curves towards experimentally measured data. And clearly the ultimate, in terms of semi-empirical equation of state, is the Hall-Petch relationship. And again, this goes back to the early 1950s that this was developed, and quite nicely it predicts a very nice and linear relationship for the yield strength of metal as a function of the initial grain size, along with other constants given by sigma I and k sub y, which have some meaning. Obviously, k sub y represents the slope of the linear relationship when we plot the yield strength as a function of the inverse of the grain diameter to the square root. So when we plot this, then clearly ky represents the slope of that straight line, and the intercept is given by sigma I. But there's no real significant physical meaning to these constants sigma I or ky. So again, it's a semi-empirical equation of state. And indeed, we can expand upon this initial Hall-Petch expression, and many people have. Here's such an expression by Brian Pickering and Terry Gladman back from the early 1960s, looking at such a formulation from multiple regression analysis, which predicts the tensile strength, in this case, for steel as a function of the initial grain size, so in very much the same way that the Hall-Petch did. But in addition, it also illustrates the influence of some chemical composition. So there is a relationship towards the manganese concentration, as well as the silicon concentration, and indeed, as well as the amount of pearlite that would be present, say, in a ferrite pearlite reduced steel. So the units in this, I must apologize, they're in tons per square inch. So back in a time period where we were in imperial units, so we need to be careful of this. And in this expression, the measurement of the grain diameter D is in inches. But nevertheless, you see the trend, right? As before with the Hall-Petch, right? As the grain diameter decreases, we see a subsequent increase in the strength, right? That goes without saying. But additionally, we have this contribution to some of our chemical composition, in this case manganese and silicon, and we can see their effects, and indeed their relative effects as measured by the coefficients in front of both of those parameters. And finally, as another microstructural parameter, we can incorporate in this expression the amount of pearlite present. So in other words, instead of the microstructure simply being a function of some grain size, in this case of ferrite, we can also incorporate the presence of the second phase, in this case, that's the second sort of part of that microstructure, in this case would be pearlite. In this case, we can see that relationship. Okay, so I think this brings me to a convenient end here in terms of a gray box approach based upon a semi-empirical equation of state. I want to take a break here now because I want to come back and look at yet another gray box modeling approach, and in this case these sets of approaches will be based upon a probabilistic sort of methodology, of which I will explain when I come back. Thanks. Goodbye.